It is my pleasure to introduce Dana Dachman-Soled from the University of Maryland. Dana did her doctorate under Tal Malkin at the Columbia University. She was then a postdoc at Microsoft Research New England. Dana has published a number of papers on several aspects of cryptography, including secure computation and security against physical attacks. Her today's talk is about non-malleable codes, which is one of the tools used in the area of the foundations of the tamper-resilient crypto. So please welcome Dana.
So thank you, Stefan, so much for the introduction. So today I'm going to be talking about a sequence of works that finally led to non-malleable codes for AC0. And I'm going to be highlighting two of the results along thank co-authors on those two papers covering, and those are Marshall Ball, Xiao Guo, Mukul Kulkarni, Tal Malkin, and Ling Tan. Okay, so let's start out with some background on coding scheme. Sender has a message X as input, and the sender is going to run the encode algorithm denoted by E on the message to obtain a code word. And then the sender will send the code word over a channel. The channel is going to select a function, little f, which we're going to call the tampering function, from some allowed class of functions, big F. And it's going to apply little f to the code word. The receiver is going to receive this tampered code word, and it's going to run the decode algorithm denoted by D in order to recover X tilde, which is the recovered message. And we want to have some guarantees between the relationship between the recovered message X tilde and the sent message X. And I just wanted to also note that this is a non-cryptographic setting, so know that there are no secret keys at all in this setting. The encode and decode algorithm are completely public, and they do not take as input any secret keys. So what type of guarantees can we expect to have about the received message? So the type of guarantees that we can achieve are going to largely depend on the class of tampering functions that we allow. So let's kind of look at the two ends of the spectrum. So on the one hand, we have error correcting codes, and these are going to achieve a very strong property of correctness. So we know that the recovered message, X tilde, is going to be the same as the message that was sent, X. However, we're going to have to restrict the class of functions F to only contain functions little f that modify less than distance over 2 code word symbols, where distance is the distance of the code. On the other end of the spectrum, we have non-malleable codes. And here, we want to allow tampering functions F that potentially modify every code word symbol. In this case, we can no longer achieve correctness, but now the relationship that we're going to achieve between the recovered message and the sent message is going to be that either X tilde is the same as X, or it's independent of X. And the desired property that we achieve in this setting is privacy. So specifically, one of the applications of non-malleable codes is to tamper-resilient cryptography. So here we're going to encode the secret key of a device using a non-malleable code, and we're going to be able to guarantee that the secret key remains private even when an adversary can tamper with the encoding. So there's been a lot of prior work on non-malleable codes. This is a very active research area in the past several years. So non-malleable codes were introduced by Dziembowski, Pietrzak, and Wichs in 2010. And in that paper, they showed several results. One important result was that they showed that it's impossible to achieve non-malleable codes against all of P, against any polynomial time tampering. So let's see why this is the case. So remember that we are in a keyless setting. So there is no secret key between the sender and the receiver, and encode and decode are public. So if we have an efficient non-malleable code, where the encode and decode functions are in P, then if we allow arbitrary tampering in P, what the adversary can do is it can simply decode the code word, change the message to a related message, and re-encode, and then forward this re-encoded code word to the receiver. And of course, we're not going to be able to achieve non-malleability in this setting. So this is going to be an important point that we're going to come back throughout the talk. And in this first paper, they also showed very strong existential results that showed that you can achieve non-malleable codes against tampering classes of bounded size. So we know that the class of tampering functions F has to be computationally limited in some way. So what are the ways that people have looked at kind of limiting these functions F? So there's been a long line of works that looks at compartmentalized tampering families. So for example, bitwise tampering. So here the tampering has to occur independently on each bit of the code word. Another popular class of tampering functions that people have looked at is split state tampering. So here the code word is split into multiple parts, and different tampering functions can be applied independently to each part of the code word. There have also been results on tamper resilience against permutations and bitwise tampering, and this is an example of a non-compartmentalized tampering class. So in this talk, I want to emphasize a more recent line of work that focuses on constructing non-malleable codes against tampering classes F that correspond to well-studied complexity classes. So I'm not going to go over all the results on this slide, but I just want to name a few of the classes that we can achieve non-malleable codes against, and I will go into more depth about some of these results. So these include bounded polynomial size circuits, various types of space-bounded tampering, and then NC0 and AC0, which are two complexity classes that I'm going to be talking about in more depth in the upcoming slides. So I want to draw your attention to the two leftmost columns here. And the reason for that is that the leftmost column is kind of the best possible setting. So in the leftmost column, we're going to consider information theoretic constructions. So there are no computational assumptions involved. We're going to require that encode and decode are efficient, polynomial time. And we are in the standard model, so there is no CRS or random oracle. And prior to the work that I'm going to be talking about, it was known how to achieve non-malleable codes in this kind of optimal setting for NC0. For AC0, there was also construction, also information theoretic, and in the standard model. However, there was a caveat, which was that the encode function was inefficient. So a message of length k would end up being encoded with a code word of exponential size in k. I also want to mention some of the subsequent work to our work, which continued on this path. So in kind of the optimal setting of information theoretic and standard model, it was shown how to get rate 1 non-malleable codes for NC0, non-malleable codes for bounded depth decision trees, and bounded degree polynomials. And on the other spectrum, where we require computational assumptions, although no CRS, together with co-authors, we showed how to get non-malleable codes for bounded uniform polynomial time tampering. So just to get ourselves familiar with some of these complexity classes that I'm going to keep mentioning throughout this talk, I want to kind of draw this visual picture here. So this outer circle represents P, polynomial time, and we know that we cannot achieve non-malleable codes for all of P. So we're going to be looking for classes that do not contain P, and we can try to construct non-malleable codes for such classes. And specifically, the type of classes that we're going to be looking at in this talk are classes that correspond intuitively to computations that take low parallel time. Okay, so more specifically, we're going to be considering various types of circuit classes. So first of all, the classes NC0 and AC0. So these are constant depth polynomial size circuits. In addition, NC0 requires bounded fan-in. So each gate has a constant number of incoming wires. And AC0, which is same as NC0, but has unbounded fan-in. So here we're going to allow any number of incoming wires in each gate. Another class that's going to be important to us is the class of local functions. So this is going to be the class of functions where each output bit depends on at most n to the 1 minus epsilon input bits. So each output bit depends on only a subset of the input bits. And finally, I want to mention the class NC1. So NC1 is a class of logarithmic depth polynomial size circuits. And actually, before I said that non-malleable codes for P are impossible, but non-malleable codes for NC1 are also out of our reach currently, because in fact, it is not known, we don't know how to show that NC1 does not contain P. We don't know how to separate NC1 and P with the current techniques that we have in complexity theory. And if NC1 is equal to P, then the impossibility results for P would apply to NC1. So if we want to restrict ourselves to constructions that are information theoretic and don't make any assumptions, then we can't even get up to NC1. We have to look inside or under NC1. And I also want to mention that there is, for the other classes that I mentioned, AC0, NC0, and local, there is actually an explicit function in P and also in NC1, which is not contained in these classes, and that is the parity function. So given an input string of n bits, output the parity of that string, that problem is outside of AC0, NC0, and local. So this gives us hope to be able to construct non-malleable codes for these classes. So prior work with co-authors presented non-malleable codes for local functions, which also includes NC0. And now the main result that I'm going to be talking about is the construction of non-malleable codes that are unconditionally secure against polynomial size and unbounded fan-in circuits of depth log n over log n. And the code length that we achieve is k to the 1 plus delta, where delta is a small constant between 0 and 1, where the input message is k bits and the output code word length is n. So I just want to note that this includes the class that we achieve includes the class AC0. It contains AC0. So remember, AC0 is a class of polynomial size unbounded fan-in circuits of constant depth. And for the case of AC0, our result actually gives a slightly better code word length of k to the 1 plus little o of 1. And I also want to emphasize that this result is essentially optimal in terms of circuit depth. This is kind of the best we can do in terms of circuit depth in the information theoretic setting. And this is because NC1, which I said we cannot construct non-malleable codes for NC1 without separating NC1 from P. And NC1 is contained in the class of polynomial size unbounded fan-in circuits of depth O of log n over log n. So if we increase the depth of circuits that we can handle in our result, then that would, if we substantially increase it, that would include NC1. So this is essentially optimal in terms of depth. And so here is a pictorial representation of the class that we can construct non-malleable codes for using this result. So this circle represents circuits that have depth log n over log n and polynomial size. I also want to mention a follow-up work. So I mentioned that our result is optimal in terms of circuit depth. It was not optimal in terms of circuit size. A follow-up work of Ball, Go, and Wichs presented non-malleable codes for bounded depth decision trees. And this is going to imply non-malleable codes for sub-exponential size and unbounded fan-in circuits of constant depth. Okay, so it's still constant depth, but now the size goes from polynomial to sub-exponential. And so pictorially, the follow-up work includes this purple circle. So everything from the prior result, and additionally, it includes constant depth and sub-exponential size circuits. Okay, so this is a good place to quickly stop for questions, if there's any questions.
I don't see any questions.
Okay, great. So I'll continue. So I'm going to start the kind of technical portion now of the talk, and I'm going to start by giving some definitions. So we gave some intuition of non-malleable codes, and now I'm going to give some formal definitions. So first, I'm going to talk about the syntax of a non-malleable code. So non-malleable code contains an encode and decode algorithm. The encode algorithm takes an input message of length k bits and outputs a code word y of length n bits. And we can assume that the encode algorithm is randomized. The decode algorithm takes in a tempered code word y tilde of length n bits, and it's going to output some k bit message. And in some of the results I'm going to talk about today, we may allow the decode algorithm to also be randomized. And we have the natural definition of correctness. So if you decode a valid encoding of a message x, then you should recover x with probability 1. So now let's look at the definition of non-malleability. So what does it mean for ENC-DEC to be non-malleable? So we're going to consider two experiments, a real experiment and a simulated experiment. So in the real experiment, we just do the natural thing. We take the message x, we run the encode algorithm, we apply the tampering function, we run the decode algorithm, and then we output x tilde. In the simulated experiment, we have a simulator which makes a draw from a distribution df, which is a distribution over a special string, same, and constant c. And this distribution df is allowed to depend on the tampering function f, but it cannot depend on the message x. So the simulator makes a draw from this distribution and outputs either the special string same or some constant c. If the simulator outputs same, the experiment will automatically replace that with the original message x, and otherwise the experiment will output the constant c. Okay, and non-malleability requires that these two experiments are indistinguishable. So the intuition behind this experiment is that the simulator has to somehow simulate the effects of the real experiment while knowing the tampering function f, but without knowing the message x. So a really nice alternative definition was given by Agarwal et al. So this is equivalent to the previous definition, but kind of another way of looking at things. So we still have two experiments here. The first experiment stays the same. This is the real experiment. And now this equivalent definition says that ENC-DEC is non-malleable if the effects of this blue box, which consists of applying enc, applying f, and applying dec, can be simulated by sampling a function little g from df, where df is a distribution over the identity and constant functions, and then outputting g of x. Okay, so we can simulate the effects of the tampering experiment by drawing a function g from a distribution over identity and constant functions. Okay, and this definition is equivalent to the previous one. So it turns out that this definition is really nice because it can now be generalized to a notion called a non-malleable reduction from a class F to a class G. And again, this was introduced by Agarwal et al. So again, we have the same real experiment, but now we're going to say that the effects of this blue box can be simulated by sampling a function g from a distribution dfg, which is now a distribution over functions in the class G. So before we had a distribution over identity and constant functions, now we're allowing a distribution over functions in G. Okay, and at the end of the experiment, we output g of x. So the first thing that we can clearly see is that if we have a non-malleable reduction from the class F to the class that contains identity and constant functions, then we have a non-malleable code, just by the definition that we gave. And another nice property is that non-malleable reductions compose. So if we have a non-malleable reduction from the class F to the class G, and a non-malleable reduction from G to H, then we can compose the two encode and the two decode functions in order to get a non-malleable reduction from F to H. So how can we see this? So we can draw these boxes as before. So we start out with the real experiment over here, just with the encode and decode functions composed. And now we can replace the first blue. So given our non-malleable reduction from F to G, we can replace the first blue box with a distribution over functions in the class G. And now we can replace the outer blue, for every little g, we can replace the outer blue box with a distribution over functions in H. And now we see that the top and bottom are still indistinguishable. And so now we've been able to replace the entire outer box here with a distribution over functions in H. So given these nice properties, the approach that we're going to do is we're going to get a sequence of non-malleable reductions from class F1 to F2 all the way to FL. F1 is going to be our target class. So in this case, it's the class AC0. And FL is going to consist only of identity and constant functions. Using the composition theorem, we get a non-malleable reduction from F1 to FL. And this implies that we get a non-malleable code for F1. So I guess I can stop for questions.
Stefan.
Yes, there is a question.
Okay, I'm looking at.
Yes.
Right. So
yes, is parity
number...
outside the purple region? That was a question from Gilles.
Yes, so parity is outside. So I think the purple region corresponded to the follow-up result of Ball, Go, and Wichs. So yes, parity is outside that box. So that's kind of all of our techniques kind of rely on the same type of techniques that are used to show that parity is not an AC0. And I mean, that work was not my work, but it uses similar techniques. And the ban on the number of compositions, well, so the error when you, these indistinguishability, there's some error associated with them. So that's going to add up. So you can handle a polynomial number. If your error is negligible, you can handle a polynomial number of compositions. Okay, so let me continue. So the outline of what we're going to do is we're going to have a sequence of non-malleable reductions. So we know that we have prior work that constructed non-malleable codes for split state. And then we're going to consider two different types of local functions that I'll describe more later, and show non-malleable reduction from these classes to split state. And then finally, we're going to show a non-malleable reduction from AC0 to this type of local function class. And the lines highlighted in red are the ones that I'm going to look at in more depth. Oops. Okay, so let me first discuss more formally what split state is, and also discuss the prior work. Okay, so I'm going to be focusing on two split state functions. They can be generalized to more split state, but here the code word is going to be split into two parts, L and R. The tampering function G is also going to have two parts, G1 and G2. And now to apply the tampering function, we will just apply G1 to L and G2 to R independently. And the idea here is that the two functions are going to act independently on the left and the right part of the encoding. So there's a long line of work on non-malleable codes for split state, starting with constructions for single bit messages, then extending to multi-bit messages, and finally improving the rate, where the goal is to finally get constant rate split state non-malleable codes. So now that we know about split state functions, I'm going to talk about the non-malleable reduction from local functions to split state functions. So let me start talking about different types of local functions. So we're going to have output local functions and input local functions. So for output local functions, we're going to define what it means to be output local. So we're going to look at the circuit representation of the function f. And then we're going to draw a graph with edges from inputs to outputs. And there's going to be an edge from input bit xi to output bit yj if the circuit for f contains a path from xi to yj. Okay, and something is going to be in local LO if the in degree, so each of these output bits has in degree at most LO. So the number of edges coming in is at most LO. And semantically, what this means is that each output bit depends on at most LO input bits. So it turns out that output local functions are already interesting for one reason, because they contain the class NC0, which is one of the class that we're interested in. In fact, local LO contains fan-in-2 circuits of depth log LO. And so for any super constant LO, local LO will contain NC0. So the result I'm going to show is actually an intermediate result. So here we're also going to restrict the functions to be input local. So again, we consider the same graph. And now a function f is going to be in local Li if the out degree, so now we look at the out degree of the input nodes, and the out degree of each input node should be at most Li. And semantically, this means that each input bit affects at most Li output bits. Okay, and then if we want something that is both input local with locality Li, output local with locality LO, we just take the intersection of these two classes. Okay, so now I can state the first subresult. We showed in our work that when you set LO and LI to square root of n, so input and output locality are square root of n, there is a non-malleable reduction from local to split state with inputs of length k and outputs of length k squared. Okay, so let's try to get some idea for how we can kind of leverage split state in order to get a result for local. So what I've drawn here is the real experiment. So in the real experiment, we get a split state code word, LR, and we're going to apply E prime, which is also split state. This is the non-malleable reduction for local to split state. And then we're going to apply the tampering function over here. And then we will apply the decode function, D prime, which is also split state. And we will get L tilde and R tilde. And in order to give a non-malleable reduction by the definition that we saw for non-malleable reduction, what we need to do is we need to provide a distribution over split state functions such that when you apply this split state function to LR, you get something that is close to L tilde R tilde. So we need to simulate the effects of the real experiment using a split state function drawn from some distribution. So how are we going to do this? So the first thing to note is that our tampering experiment is itself already somewhat close to a split state function. Most of the functions here are acting either only on the left or only on the right. The only thing that's messing us up is these crossover edges from right to left and from left to right. And so what we want to show is that we can actually sample the values of these crossover edges. So the value of the nodes that these edges are adjacent to, we can sample them from a distribution that is independent. So the right to left crossover edges can be sampled from a distribution independent of R. The left to right edges sampled from a distribution independent of L. And once we fix these values, then we can view the entire tampering experiment as a split state function in L and R, which is our goal. So the distribution over functions comes from choosing these edges from a distribution. Once we do that, we have a split state function. Okay, so let's first look at the case of the edges that are crossing from right to left. So in this case, we're going to play a trick where we're going to increase the size of the right side. So make the right side a lot larger than the left side. And because we know that our tampering function is output local, we can bound the number of these red edges crossing from right to left by the size of the left-hand side, so the number of bits over here, times LO. That's due to the output locality. And we're going to set our parameters such that the size of the left-hand side times LO is a lot smaller than the size of the right-hand side. So why is this useful for us? Well, we're going to use a special encoding, E prime R, D prime R, which is a reconstructible probabilistic encoding. So it's an error-correcting code, which has some additional properties. And the additional property is that for constant C, any C fraction of bits of the code word are uniformly distributed and do not depend on the encoded message. This type of encoding also has another property, which is why it's called reconstructible, but that only comes up in the proof, so I'm not going to discuss that. So why is this useful for us? So remember that we said that the size of the left-hand side times LO is a lot smaller than the size of the right-hand side. So as long as the size of the left-hand side times LO is less than C times the size of the right-hand side, then we can actually simulate all the edges going from right to left just by setting these values uniformly at random. That's the property that this code gives us. Okay, so we've successfully handled the edges going from right to left. What about the values going from left to right? So now the strategy from before is going to fail. So we can only use our trick once. So we made the right-hand side larger than the left-hand side to deal with the first one, but we can't keep doing this. So we can't solve this in the same way as before. So how are we going to deal with this problem? So the first thing that we're going to do is we're going to make use of our second assumption, which is the bounded input locality, Li. So what that means is that for the number of edges going from the left to the right is going to be at most Li times the size of the left-hand side. And remember, since the right-hand side is a lot bigger than the left-hand side, what this means is that there are many positions on the right-hand side that are safe. So what does it mean by safe? It means that for many positions on the right-hand side, there are actually no incoming edges. And so we can figure out the value of these positions just using a split state function that depends only on R and not on L. So the idea would be is that when we decode, when we apply d prime R, we only decode based on the safe locations. We ignore the other locations. We only decode based on the safe locations. And now we can represent decode as the decode of the tampered code word as a split state function that depends only on R. So the problem, of course, with this approach is that if your decode function cannot adaptively depend on a tampering function. So we need to construct a single non-malleable code or non-malleable reduction E prime dr that works for every tampering function. We can't first fix the tampering function and then choose a d prime that works for that tampering function. So this doesn't quite work. So how are we going to solve this problem? So the solution is going to be to switch from a real decode to a simulated decode. So the actual non-malleable reduction will use a decode function that does not depend on the tampering function. Simulated decode will depend on the tampering function. And we're going to show that we can maintain consistency between the two, so the two experiments will be indistinguishable by doing a small number of consistency checks, which will ensure that we get the same output from the real decode and the simulated decode. And this is actually similar to techniques that we used in a much older work from 2008 on non-malleable encryption. Okay, so just to review what the real decode and simulated decode will do. So the real decode is going to reconstruct the nearest code word wreal to w prime using everything, using all the blue locations. So that's the natural thing to do. It will use all the information that it has in order to decode. And then it's going to do these random consistency checks at the green locations to check that the nearest code word wreal agrees with w prime. And the key is going to be that we only have to do a small number of consistency checks in order to ensure that wreal and w prime are very close to each other. In the simulated decode, we are only going to use the orange locations, which are the safe locations that have no incoming edges from the left, in order to reconstruct wsim. And these blue locations that have incoming edges, we're just going to treat them as errors. And we'll tolerate them because we are an error correcting code. And we are again going to check that wsim agrees with w prime at randomly chosen green locations. And note that the green locations that are chosen may not be safe. So green locations may have incoming edges from the left. However, However, there's only a small number of green locations. So how do we simulate? D double prime? So note that the values at the orange locations depend only on the right-hand side. They don't depend on the left-hand side. So this is good. This is already split state. And the green locations may depend on the left-hand side, but we're going to set the parameters so that the number of green locations times L0 is at most C times the size of left-hand side. And so by the properties of the RPE, this means that we can actually leak this information. And so here we're again using the bounded output locality to say that there's only a small number of locations that we need to open on the left-hand side. And so we can just simulate all the information needed for the green locations. Okay, so now we've chosen the values of the right to left crossover edges uniformly at random. We've chosen the values of the left to right crossover edges to green locations uniformly at random. And once these are fixed, we can express L tilde and R tilde as a split state function of L and R by using the alternate decoding function D double prime. Okay, so I'll take questions again at this point.
I don't see any questions.
Okay.
So let's maybe wait for 3 more seconds. Okay, I think you can go ahead.
Okay, so there's one missing step in this sequence that I see there's one question actually that just popped.
Yes, there is one question from Maci. So do you decode from green only?
We decode from safe positions and green in the simulated decode. So anything that's a safe position, it doesn't have an edge at all, or green, which may have an edge, those are the only ones used in decode, in simulated decode. Okay, so let me move on. So there's one step that was skipped, so that I'm not going to show in this talk. So going from input-output local to output local. So this is possible to do. I'm not going to go into the details. And I also want to mention that the construction that I presented has a randomized decode algorithm. So the green positions are chosen at random. They're different each time you run decode. But you can also get rid of that assumption as well. And the original work as well as other works were able to get deterministic constructions for output local tampering. So I want to move on to the last part of the talk, which is the non-malleable reduction from AC0 to local. Okay, so in this work, we showed that for AC0 circuits of depth at most log n over log n and size at most n to the log n, there is a non-malleable reduction with input length k and output length k to the 1 plus epsilon from AC0 to leaky local. So I won't really talk about leaky local. It means that we're also allowed to leak some bits of the code word from the local non-malleable code. Okay, and this is an output local non-malleable code with locality k to the little o of 1. So the actual construction is a recursive construction, and each level of the recursion is going to correspond to a different non-malleable reduction that reduces the depth of the tampering circuit by 1. So this has to be done log n over log n number of times in order to get the full construction. And I'm only going to be talking here about the bottom level. So the bottom level is going to be the reduction from depth to circuits, which are CNF and DNF. So an OR of ands or an and of ORs to the leaky local class of functions. So let me mention the high-level ingredients. So we're going to use the local non-malleable code that I mentioned from previous work. with n to the epsilon output locality. And we're going to be using the RPE again that we had before. So remember, this is just an encoding that remains private, so it doesn't leak any information about the message, given any C fraction size subset of the code word bits for constant C. And the other high level ingredients that we're going to use, so this is what I kind of alluded to. So these are ingredients that are also present in the proof that parity is not contained in AC0. So we're going to use a variation of the switching lemma of Hastad. So the switching lemma says that if you take a T width, CNF or DNF, so this is a depth 2 circuit, with the number of variables in each term is at most T, and you hit it with a random restriction. So I'm going to talk more about what a random restriction is, but basically you're going to set some of the input bits to 0 or 1 at random. So if you hit a CNF or a DNF with this random restriction, then you're going to collapse to a T depth decision tree. And here we should think of T as epsilon times log n. So this is what a decision tree looks like. So at each step, you look at a different variable, and then if it's 0 or 1, you go right or left, and you proceed through the tree. At the bottom, you output either 0 or 1. For each path, you have a different output. And the main thing to notice is that decision trees of depth epsilon times log n are actually n to the epsilon local functions. And the reason for that is that if it has depth epsilon times log n, since it's a binary tree, the number of nodes in this tree is going to be at most n to the epsilon, which means that we only ever look at n to the epsilon variables. So this decision tree is also a local function. And in fact, we're not going to use the switching lemma itself. We're going to use a pseudorandom version. So pseudorandom switching lemma. So Trebizond and Shu proved that the switching lemma still holds when the random restriction that we hit the CNF or DNF with is sigma-wise independent. So let's look at more closely at what these random restrictions are. So the random restriction is going to have some parameter P. And this P is going to be the probability that, so we're going to go bit by bit. With probability P, we're going to choose that location to be a star. That means we leave it alone. It means we don't change the variable in that position. And with probability 1 minus P, we're going to set it to 0 or 1 at random. Okay, and this is a random restriction with parameter P. We can view this restriction in another way, which is equivalent. And the other way we can view it is that we kind of first sample all of the randomness, and then we apply a deterministic function to the input. So we're going to first sample a set S of random locations using randomness R, and these are the locations where we're going to put stars. And we're also going to sample a 0, 1 vector with randomness R prime. So these are the 0, 1s that will go in the non-star positions. And then we just go bit by bit. And if we're at the ith bit and I is not in the set S, we're going to set it to the next random value. And if I is in S, we're going to set it to star. Okay, so now we can see what a pseudorandom restriction is. So in a pseudorandom restriction, we want to take the second view of how to sample a random restriction. And it's going to be sampled in the same way as we do before, except that before R and R prime, the randomness for sampling the set and the values of 0, 1 were uniform random. But now we're going to choose R and R prime so that they're not uniform random, they're only sigma-wise independent. And this means that we can generate R and R prime using a short seed zeta. Okay, and then as before, we're going to sample a set of locations and sample values using these sigma-wise independent randomness R and R prime. Okay, so now let's see what's going to happen. Let's try to actually get our non-malleable reduction. So in the first attempt, we're going to not even use the pseudorandom restriction. We're just going to try to use a random restriction and see what happens. Okay, so we're going to first encode our message using our local non-malleable code. And we're going to get a code word X, which has bits X1 to XK. And then when we run our non-malleable reduction, the encode of the non-malleable reduction is going to simulate a random restriction where each star position of the random restriction is going to be replaced with one of the bits of this encoding, and the random 0, 1 positions will just be set to 0 or 1 at random. Okay, so the encode algorithm of the non-malleable reduction is essentially simulating a random restriction. It puts code word bits in star locations, and it puts 0, 1s in the other locations. Okay, and now this is a picture of the tampering experiment. So this box here is a very complicated CNF or DNF, where all the output positions depend on all the input positions. But because of the switching lemma, we know that when we apply this, essentially apply this random restriction during encode, what's going to happen is that this complicated CNF or DNF is going to collapse into these local functions. Okay, and this seems very useful because now we have a non-malleable code for local functions. So it seems like we have a non-malleable reduction. But there's still a problem with this construction, and that is that now we don't know which bits to decode. So remember, the star positions are the positions that contain important information about the code word. The other positions are just random 0, 1 bits. But now we've lost this information. It was used during encode, but we've lost it during decode, and we don't know how to decode this. We don't know which positions are relevant and which positions are just random 0, 1 values. So the solution is going to be to use a pseudorandom restriction instead of a random restriction. So now what we're going to do is we're going to run the local encoding algorithm to generate the code word X, which has bits X1 to XK. And we're also going to choose zeta, which is the seed for the pseudorandom restriction of the switching lemma, of the pseudorandom switching lemma. And we're going to encode this seed using an RPE. And we get R1 to Rm. And now we're going to append these values R1 to Rm to the code word. And now when we encode, we're going to use zeta in order to generate the pseudorandom restriction. Again, we're going to place the X1 to XK values in the star positions. The other positions are going to be 0, 1 at random. Okay, and now we have what we need to apply the pseudorandom switching lemma because the blue positions are sigma-wise independent because of how we chose the parameters for the pseudorandom switching lemma. And R1 to Rm are also sigma-wise independent because this is a property of the RPE, which says that any constant number of positions are uniform random. So now we can again apply the pseudorandom switching lemma, and now we collapse down to these local functions. And finally, we can now simulate everything. So how will we simulate the effects of the tampering function using local tampering? So in the simulation, we're going to choose the seed zeta, and we're going to choose random values for the yellow positions. We're going to fully compute the values of the green output positions using the same trick as before. Because we have good output locality, we can afford to leak all of the input bits because there's only a small number of green positions. Once we learn this, we learn the tampered seed data, which allows us to figure out which positions are the star positions. So the red positions are the star positions. They're the ones that we care about. And now we have a local tampering functions with the correct size input and the correct size output. So the local tampering function that we've reduced to is the local function that is restricted to the gray inputs and the red outputs. And that is the non-malleable reduction to local. So I just want to end with, so I guess let me just take questions if there's any question and then wrap up.
Are there any questions now? Let's wait because maybe someone is typing. Okay, I think there are no questions. You can go ahead.
Okay. So I just wanted to end with some discussion and open questions of kind of what are the interesting things left to do in this regime. So I think the obvious question is, can we get non-malleable codes for more types of tampering classes? So note that, as I mentioned before, anything that's kind of beyond AC0 is going to require some kind of computational assumptions if we want encode and decode to be efficient. And that's because for classes beyond AC0, we don't know how to separate them from P. And I also just wanted to mention a late breaking result, which was just submitted to ePrint. It's either already there or will be live in a few days, which is together with Ilan Komargatsky and Rafael Pass. And this result achieves non-malleable codes for all polynomial size tampering circuits with bounded polynomial depth and no CRS, but it does need computational assumptions, some of them pretty strong. And so in general, it's interesting to see, we need some computational assumptions, but can we get non-malleable codes for larger classes of tampering functions with kind of minimal computational assumptions? And since this is ITC, Information Theoretic Cryptography, I also wanted to mention the question of obtaining non-malleable extractors for these various types of complexity classes. So non-malleable extractors are similar to non-malleable codes. They actually imply non-malleable codes, but the parameters of the non-malleable extractor will affect the parameters of the non-malleable code. So for example, for AC0, the result of Chattopadhyay and Lee achieved their non-malleable codes for AC0 going through a non-malleable extractor, but the parameters are not optimal. And for some of the other complexity classes, we also do not know of non-malleable extractors for these classes. And I also want to mention that the recent result of non-malleable codes for bounded degree polynomials also goes through a construction of non-malleable extractors and then uses that to get non-malleable codes. And then finally, the last question that I wanted to mention is binding applications of these types of non-malleable codes, so non-malleable codes for various complexity classes, to other areas of cryptography. So kind of what can they be useful for in cryptography other than tamper-resilient cryptography? So there has been quite a bit of success in applying bitwise or split-state non-malleable codes to obtain improved constructions of non-malleable encryption and non-malleable commitment. But as far as I know, there haven't been similar results for these complexity class non-malleable codes. So with that, I guess I'll end, and I'm happy to take any questions.
Okay, so let's thank Dana. Are there any questions?
I have a question if we're waiting for people to formulate questions in the Q&A.
Sure.
So what are, in terms of places where we know explicit, where we know non-explicit, like say probabilistic constructions versus, you know, settings, but where we don't have like explicit constructions?
Mm-hmm.
Are there, what are the, you know, where are the kind of big open questions there? So I recall this work of, you know, Chiragchi and Guruswamy and maybe some others that you mentioned that showed some basic existential results also.
Right.
What the, like, what the state is there.
Right. So if you just want existence results, we kind of know it for very, very large classes of tampering functions. So as long as the class is kind of slightly smaller than the total possible number of tampering functions, then we can get these existential results. I think the ones you're referring to are for bounded polynomial size tampering. So there's also randomized constructions, but they can be kind of de-randomized using a CRS. So we have so there are constructions known for polynomial bound tampering in the CRS model, and we had some follow-up work with that, which does not require CRS but has computational assumptions. So yeah, I guess that's a good question. I don't know if there's any reason to think that that it would be impossible to get information theoretic non-malleable codes without CRS for bounded polynomial tampering. So maybe others can speak up if they know a reason why that should be impossible, but I guess that would be a huge question.
Thanks. Anat has a question. Maybe she could speak up.
Yes. Yes, I should. How do I do it?
You can unmute herself.
She can unmute herself. Okay. Anat. Okay. Ask to unmute. Maybe I can.
Unmute. Yeah.
Okay.
Can you hear me? Yeah. For some reason it's working for me. Okay. Good. So I was just wondering if there is some provable separation between the deterministic decoding and the randomized decoding model.
Yeah, that's a great question. So actually, the original definition required the deterministic decoding. And I think for cases where you have encryption or where there's a secret key, it's kind of without loss of generality because you can use a PRF to simulate that randomness. We were actually not sure if they are equivalent for non-malleable codes, for the non-malleable code setting where there's no secret key. Our first construction used a randomized decode, but then we were able to remove this randomness and get a deterministic decoding. So I don't think we know any examples where the decode has to be randomized, but it could be possible to separate them.
I see. Okay, thanks.
Sure.
Okay, Maciej had a question, but now he wrote, "Forget my last question." So I guess we can forget it. Are there any more questions?
Because I have a sort of an open-ended question, but it seems like it's significantly harder to get non-malleable codes than it is to just prove circuit lower bounds or some sort of like come up with a function that cannot be computed in some class. But it seems like a necessary like prerequisite. You need to come with a function that the class cannot compute. Do you think that would be possible to somehow do it almost generically, like some generic idea to say if a class can't compute a function, you can also design a non-malleable code for that class? Or what's the main hurdle or difference between these two problems?
So I guess we do have a result that I didn't talk about. It's in the CRS model and computational assumptions, which kind of shows that classes for which we have average case hard problems, we can get non-malleable codes for. I mean, the formal result doesn't quite show that, but that's kind of the spirit of the result. But we also needed kind of additional stuff on top of that. I think the main issue is that hard problems kind of seem to give you some kind of secrecy, but it's not clear that they give you non-malleability. So going from like something that's hard to compute to some kind of non-malleability guarantee, it's not exactly clear how to do that. It's kind of a similar problem as like semantically secure encryption to non-malleable encryption. And that was kind of the ideas that we used in our result. But that required a CRS and computational assumptions.
Mm-hmm. Is there anything known for like space-bounded computation or other, classes that for which we do have like hardness results, and where the things that are hard for that class don't necessarily, like, they have to lie outside the class, obviously, but maybe they're hard by going off in some different direction, like using a lot of space but not a lot of time or something like that.
Right. So we also had a result on space-bounded and streaming algorithms, which uses like some of Ron Raz's work on like computing parodies or learning parodies. And I think there's also work on space-bounded tampering in the random oracle model. But yeah, I think like any class that doesn't contain P is either provably or by conjecture is a good candidate for non-malleable codes.
I think Sebastian had some paper on this, right? Sebastian and his students had a paper on non-malleable codes in the space-bounded model.
Yes, I think I cited it on one of my slides, but I don't
yes, it was on your
document.
slides. Yes, are there any more questions? I hear some noise from Anat.
No, sorry, that was the door slamming.
Okay. Okay, so I guess there are no more questions. So let's thank Dana again.
Thank you.
And now we have